with the basics of mechanics in the last lecture, so we will continue with that today. Okay, so we had seen the definition in general of waves, especially mechanical waves, that any phenomena involving the propagation of mechanical energy and information by oscillations of medium particles, such that the mean position of the medium particles remains fixed, but by oscillating it about their mean position, they transfer energy from point to point, and hence information or energy is propagated from one point in space to another through a medium without actual displacement of medium particles. Okay. Yeah, they do displace in terms of their oscillations, but their mean positions remains fixed. Okay. And then we had gone on to discuss things like the classification of mechanical waves into longitudinal and transverse waves, etc. And then we had reached a point where we were looking at the mathematical equation of a function which has a graph that moves with respect to time along the x-axis. So today we'll understand why that is important, because we're going to start by understanding the general equation of a one-dimensional transverse wave. So let's understand this. So one-dimensional, that means it's traveling along one axis. Okay. Transverse mechanical waves. The physical model of that is going to be waves on a string, on a stretched string. So first and foremost, we will see how to develop a mathematical model of this. So the general equation of such a wave, which is basically a mathematical model of it. Okay. So if we take the x-axis as our medium, or in this case the stretched string, and we assume that the x-axis is, one end is going to infinity, the other end is over here. So if this represents a stretched string, which has, let's say, a tension T, which is uniform, and a linear mass density or mass per unit length, which in this chapter we will denote with the symbol mu, even though we are more used to denoting it with the symbol lambda, but here lambda will have a different meaning. Okay. So now in this, if we create a disturbance by giving energy at one end, like we pluck the string at one end, okay, and so we create a pulse. So what we will notice is that because of the elasticity of the string, what will happen is that the energy that we've given, it's caused the string to get deformed and form this kind of a shape where, you know, this part is under stress and strain, this part is under stress and strain. Okay, so this is strain, okay, because we have created a pulse. So as a result of that strain, what happens is that these particles tend to pull up the particles next to them. So in the process, these go up like this, whereas these are trying to retain their original shape, so they tend to come like this. So in after a bit of time, this pulse has shifted like this, and then after a bit of time, it has shifted like this, and like this pulse keeps shifting with respect to time. So this is where the pulse was present at some time t, then after some time the pulse has shifted to t plus delta t, and this shifting happens at a constant rate v. Okay, so any disturbance, any transverse disturbance, okay, So what that does is it creates a displacement along the y-axis, along the transverse axis, which is perpendicular to the medium, which is along the x-axis. It creates displacement along the y-axis. At any point on the medium x equal to x. Okay. So any transverse disturbance tends to travel or propagate along the medium. Okay. Which in this case is the stretch string. At a uniform speed v, and this speed depends on the medium's physical properties, which are going to be later we'll see in more detail, the tension and linear mass density. So depending on how much tension the string has and how much inertia it has in the form of linear mass density, that these two parameters will determine how fast this disturbance travels. Okay. So this transverse disturbance creates a displacement which becomes a function of x and t. Okay, such that the pulse, so-called, travels at a uniform speed. Okay. Now I will just step aside this from a moment to what we were seeing last time. So last time we had seen about transformation. I'll come back to that, don't worry. Okay, so transformation of graphs. What we had seen is that if we have any function y equal to fx, whose graph looks a certain way, now if we replace x with x plus d, for example, then the graph shifts towards the left by a distance d. Or if we replace x with x minus d, then it shifts towards the positive x direction. Okay. So this is about a math function, okay, where x and y are numbers. For example, y is equal to sine x, or y is equal to e raised power x, or something like this. Okay, but if x represents position, okay, in meters or centimeters or whatever, so x has a physical dimension of length. Okay, then the parameter applied to the function, or what we call in maths language the argument of the function, must be kx, where k is a constant of dimension 1 by L. Okay. So for example, y would have to be written as a sine kx if dimension of x is L. So dimension of kx must be 1. So k must be a constant having dimension L inverse. Because as you know from units and dimensions, we cannot operate the sine function directly on quantity which has unit or dimension. It has to be applied on a quantity which is in radians or is dimensionless. Okay, here x is dimensionless, it's a pure number. Y is dimensionless, it's a pure number. Okay, and if y also has the dimension of length, then a has to be a constant which has dimension of length. Okay, so there is that distinction. So just make a run through of the concepts that we've discussed up to here, then we'll come back to general equation of a traveling wave. Okay, so in general, we have to express it like this. It has to be a function of k into x. If x has the dimension of length, so dimension of k into x should be that it's a pure number. It's dimensionless. Yes, I'll scroll up. Okay. Okay, so the difference between just writing a pure mathematical function y is equal to fx, where x and y are both pure numbers and therefore dimensionless, and writing a physical equation between two physical parameters y and x is that we have to take care of the dimensions also. So for example, if we are writing y as a function of x, then we cannot operate any function like sine, exponential, or any such mathematical operation directly on x in meters or centimeters. We have to multiply the x by a suitable constant which has the dimension of length inverse, so that it becomes a dimensionless parameter. Okay, or the argument of the function becomes dimensionless. So now when we transform this function, so to transform, for example, let's say to the positive x direction by a distance d, we have to do this operation f of k of x minus d. So therefore, from this we understand that the general equation of a traveling wave. So therefore, what we understand that if we have a stationary shape like this, this represents y as a function of x, where x is in meters or centimeters or whatever. X's dimension is L. Okay. But if we now replace this with x minus vt, where v is a constant velocity and t is time, then the same thing. So this is basically, this is the equation of a stationary shape. But this now becomes the equation of a traveling shape. Becomes a traveling graph. This traveling at the speed v along the positive x-axis. So omega is a constant. So this is a traveling shape. It travels or propagates along the x-axis at constant. Okay, so it is a constant such that its dimension is time inverse, just as k is a constant whose dimension is length inverse. अच्छा हाँ ठीक है, थर्सडे 5:30 के बाद करेंगे, 5:30 तक लेक्चर रहेगा, ठीक है। हाँ नहीं, या उनके बोल दीजिए मेरे से कोऑर्डिनेट कर लेंगे सब, ठीक है, डायरेक्टली मुझे मैसेज करके कोऑर्डिनेट कर ले सकते, ठीक है। थर्सडे इवनिंग पक्का चलेगा, बोल देना ही इज अवेलेबल, प्लीज कंफर्म विद हिम फॉर टाइम। Okay, so Snigita, I hope this part is clear now.
Yes, sir.
Okay. So transformations of graphs, it's a very normal thing in maths, but when we are applying it to a physics equation, we have to just take care of the dimensions also. That's the added thing. So now we can see that this equation, it represents the general equation of a traveling one-dimensional transverse wave. Okay. But it's traveling along the positive x-axis at speed v equal to omega by k. But likewise, if we have a function like this, y is equal to f of kx plus omega t, then this also represents a traveling wave, but this is traveling along negative x-axis. That is the only difference. Okay, but at uniform v equal to omega by k. Okay, so let us understand some examples of this. So what we notice is that for a function of the type y is a function of x and t, but for this to represent a traveling wave, okay, the argument of the function, that is what the function applies to, must be kx plus or minus omega t. So in other words, we can say that, okay, y is some kind of function of an argument where the argument of the function theta must be of the type kx plus or minus omega t. It must be linear. The argument must be linear with respect to x and t. If it satisfies this condition, then we can say that it represents, mathematically, it represents a function which is traveling along the x-axis at a constant speed. So physically, it represents a traveling one-dimensional wave. It represents a transverse one-dimensional traveling wave. Okay. Now there are some more constraints on functions also. We will discuss about that also. So it's not that we can use any and every function of this type. There are some other limitations. So we will come to that also. Okay. Okay, so now as far as such a limitation is concerned, before we get into that, let's see a couple of examples. Let's say this is a function that we have. Okay, Vaishnavi, I'll scroll up.
Done, sir.
Okay, so let's come to this example. So this is such that y is in millimeters, let's say. Okay, x is in meters, p is in seconds. Okay. So first of all, plot a graph of y versus x at the time t equal to 0, and again at the time t equal to 20 seconds. Okay, compare the two, okay, and determine the speed of this traveling pulse. Compare the above equation with the standard or with the general equation. Y is f of kx plus minus omega t, and from that determine k omega wave speed v and the direction of propagation. So just try this out, people. So basically you start here by understanding what the graph of this kind of parameter looks like. If you had a function which is of this type, e raised by minus theta square. So with respect to theta, how that function will look. And once you understand that, it will be quite easy to plot this graph. You just replace theta with the given argument, which is of the type kx minus omega t, where k and omega's values are pretty obvious in proper units also. Okay, so you can see that this function has a local cum global maxima of 1 at theta equal to 0, and it asymptotically drops to 0 as theta tends to plus or minus infinity. Okay. So over here now you can see that this function will have a similar kind of shape. So for example, we want to plot the graph of y versus x at t equal to 0. So just substitute the value of y at t equal to 0. So it becomes this kind of a function of x. It becomes so it's got the peak of 5 millimeters at x equal to 0. Like this. So it's peaked at 5 millimeters. And for example, at x equal to, now this x is in meters. So for example, at x equal to 1/20th of a meter or 5 centimeters, you can see that this value would have become 5 by e square, because this term would have become 1. By the time it's 10 centimeters. Become like this. E is approximately 2.7. Now simultaneously, if so the original function, remember, was 5 e raised power minus of 20x minus 0.01 t whole square. So now if I plot the function again at t equal to 20 seconds, I'll see it becomes like this. Okay, so the peak shifts to the point 0.01 meters or 1 centimeter. Okay. At x equal to this value, the argument of the function becomes 0. So y becomes plus 5. So the whole graph has shifted something like this, let's say. So you can see that it is shifted by delta x, which is equal to v into delta t. Now this is at 20 seconds. So the v is equal to, so according to the graphs by comparison, you can see that it shifts 1 centimeter in 20 seconds. So that is The second thing, you're understanding by the comparison of the graphs or comparing the shape at the two given times, t equal to 0 and t equal to 20 seconds. You can see how much it has shifted by. So from that, you are estimating that the velocity is so much. Okay, now at the third question, you can also understand this by comparison with a standard equation. General equation of a traveling wave is a function with an argument, which is of the type kx plus or minus omega t. So that in this case is 5 e raised power minus of 20x plus minus 0.01 t whole square. So you can see that the function is basically this, and the argument of the function is basically this. In this case, the argument of the function is 20x minus 0.01 t. So k is 20 meter inverse because x is in meters and time is in seconds. Okay. And omega is 0.01 second inverse. So from this, you can see that the wave, or in this case, the pulse, travels along positive x-axis, which the graph above is also showing you, at the uniform speed of omega by k, which is 0.01 divided by 20. This will be meters per second. So it is 10 raised power minus 2 upon 2 into 10 raised power minus 1. So that is 5 into 10 raised power minus 4 meters per second. So that is 0.05 centimeters per second. And that is what we had seen above also from the graphical method. Okay. So this is just to get used to this kind of an equation where y is a function of two parameters, x and t, and the two parameters are linked to each other in such a way that the argument of the function is either kx plus omega t or kx minus omega t. For that matter, it can be omega t minus kx also. It need not be kx plus omega t. So it can be a function of this type, kx plus minus omega t, or it could also be a function of this type, omega t minus kx. They're all the same things. But if the sign between kx and omega t is positive, then it's traveling along the negative x-axis. And if the sign is negative, then it's traveling along the positive x-axis. Okay, so now that we have understood with an example about this general equation, let's look at some more things about interpretation of this before we come to more questions. Okay, so y is equal to f of kx plus, or it can also be written like this as we have discussed. Doesn't matter how we write it. General equation of one-dimensional transverse wave. Now there are, so since this is basically a function of x and t, y is not a monovariable function. Okay. And also, unlike something you've seen before in, let's say, something like electrostatics or gravitation or something, where potential is a function of position, so it's a function of x, y, z. But here the two parameters, as I said, one of them is a spatial parameter or position parameter x, and the other is a time parameter. The other is not a position parameter. Okay, so it's a bit different. So we have to learn to interpret this accordingly. So the interpretation of this is in two ways. Okay, so let's discuss interpretation. General equation. So one way to interpret it is that if we freeze the value of time, like we had done in the two graphs that we talked about earlier, at t equal to 0 and t equal to 20 seconds or whatever, if we freeze the value of time, so what we get in that case is we get what is called a snapshot picture. So for example, at t equal to some t naught, which is a particular instant of time, okay, then what happens is that y at t equal to t naught, it just becomes a function of x. It's no longer a double variable function, okay, because t naught has become a constant. So this function's graph now represents what we call the snapshot. It's like an image of the moving graph that you've taken at that particular instant of the time. So it's a snapshot of the wave at the instant t equal to t naught. Okay. So if you freeze the value of time, it gives us a snapshot image. So it gives us y versus x at that particular time. Okay. Whereas on the other hand, if you fix x, okay, so at let's say x equal to x naught, so this represents a particular position on the x-axis, which is nothing but the medium. So it is a particular position on the medium. So basically, you're looking at a particular particle okay, on the stretch string. Which is at the position x equal to x naught. So then when you freeze the value of x or fix the value of x as x naught, what happens that the function that we have got, it is no longer a function of x, it is a function of time. So this function now represents the transverse displacement y of a particular medium particle. X equal to x naught as a function of time. Okay, so fixing the value of x, what it does is it gives us the y versus t for a particular point in the medium, or for a particular particle in the medium, it gives us the transverse displacement as a function of time. So these are the two different ways of interpreting this. Okay, so we will discuss this with examples also. For example, we have already seen that snapshot picture interpretation of that exponential pulse kind of shape that we were discussing in the previous question. We had seen two snapshot pictures and compared them. The snapshot picture at t equal to 0 and the snapshot picture at 20 seconds. And comparing them, we had seen that the shape remains the same, but it has shifted by 1 centimeters in 20 seconds or whatever. And from that, we were able to understand more things about the equation. Okay, so that is the first thing. Now the other thing is that in this interpretation, if the function happens to be a periodic function, example, a sinusoidal function, okay, or another form of a sinusoidal function, or something like this, then the equation represents a periodic wave. So what this periodic wave business means is that if you look at the snapshot picture, y at a particular time is a function of x where f is periodic. Okay. Or if we look at the y versus t at x equal to x naught. So y at a particular position is a periodic function of time. Okay. So in terms of interpretation, it means that a periodic wave has these two properties, that the snapshot picture, it looks like is a periodic shape of y with respect to x. And this thing means that this represents an oscillation. So that means medium particles oscillate with definite time period, frequency, and amplitude. Whereas this means that the snapshot picture is a periodic shape, so it has a fixed, what we call wavelength, which will denote with the symbol lambda, and we'll come to that later, what that means exactly. So if the function is periodic, and these are examples of that, then the equation represents a periodic wave. Okay. Whereas on the other hand, if the function is non-periodic, it does not represent a periodic wave. It represents a single pulse. And you can just think of the example we did of that exponential function to think of how that is different from this. When you look at the exponential pulse example that we saw, you saw the snapshot picture is not representing a periodic function of y versus x. So it does not have any wavelength. Similarly, if you fix the value of x, you will get y versus t, which will be a non-periodic function. So that means a particular position on the x-axis, it is not doing a oscillatory motion up and down. It is just having a one-time motion. As the pulse is passing through, it goes from 0 to 5 millimeters or whatever that amplitude was, and then it comes back to 0. It's not periodically going up and down with a definite frequency and time period. Okay. So that will be the second type of situation we'll see, where the function is non-periodic. But if the function is periodic, like the two examples I've shown you here, then the equation represents a periodic wave. And that means that both the snapshot picture has a periodicity, and the time variation of any particular particle's motion also has a periodicity. That means every particle is oscillating with a fixed time period and amplitude. Okay, so let us understand this with an example. So if we have a function, let's say like this, where x is in meters, t is in seconds, and y is in millimeters. So first of all, compare with a general equation, and determine k omega v and direction of propagation. And secondly, plot the snapshot y versus x at t equal to 0, t equal to 1/40th of a second, or that is the same thing as 25 milliseconds. And then again at t equal to 1/20th of a second, or 50 milliseconds. Determine the wavelength lambda, that is crest to crest or trough to trough. Okay, of the wave shape. And third, plot y versus t for the particle at x equal to 0, x equal to 1 meter, x equal to 3 meter. Okay. Show that any particle oscillates. Okay. Find time period, amplitude, and frequency of oscillations. Okay, so there's a bit of simple harmonic motion also thrown into this question. Okay, as you do it, you will realize. Okay, so first of all, we can see that the given equation, when you compare it with the standard equation of the wave, you can see the values of k and omega, and also you can see that the algebraic sign between them is negative. So if you compare with the standard equation, k is pi by 6 radians per meter because x is in meters, and omega is 10 pi radians per second because t is in seconds. Okay, so therefore v, which is omega by k, becomes 60 meters per second. Okay, and the wave is propagating along the positive x direction. So that is the first part. Okay, now you come to the snapshot pictures part. Okay. So snapshot picture at 0, 25 milliseconds and 50 milliseconds. You can understand from this. This kind of a graph. So y versus x. X in meters, y in millimeters. At t equal to 0, that graph will look like a cos square graph. Typically something like this. You can see that. You can see that this point is where the argument becomes pi by 2, so it's 3 meters. And this is where it becomes pi, so this is 6 meters, 9 meters, and so on and so forth. Okay. Now, at t equal to 25 milliseconds, you can see this term will become cos square pi by 6x minus. Now, this omega t term is 10 pi into t. So, omega into 25 milliseconds is 10 pi into 25 by 1000. So it is pi by 4. Okay, so this becomes minus pi by 4. So the cos square function or something like this. At 0, the value is cos square pi by 4, so that's half. But for example, at x equal to 3, it becomes pi by 2 minus, okay, so it becomes This is at 25 milliseconds. Okay. Now we can also see that this peak point would have shifted to 1.5. So the graph has shifted by 1.5 meters for a time interval of 25 milliseconds. Now, similarly, when you want to plot the graph at t equal to 50 milliseconds, you can see you'll end up plotting this kind of graph, because omega into 50 milliseconds will be pi by 2. So that is 10 sine square pi by 6t. So this shift is a shift of 3 meters in 50 milliseconds. Now you can also understand from this that this distance is one wavelength, which is the same thing as this distance, which is the same thing as, let us say, this distance here, or same as this distance here. So the wavelength, peak to peak or crest to crest or trough to trough, is 6 meters. Okay, now let's look at the third part to understand the periodicity of the oscillation of the medium particles. Okay. So y versus time at x equal to 0, you can see is a 10 cos square 10 pi t kind of graph. Okay. Similarly, y at x equal to 3, sorry, x equal to 1 is 10 cos square. We can write this as 10 pi t minus pi by 6 because it's a cos square function. So cos square of a minus b is the same thing as cos square of b minus a. And similarly, y at x equal to 3 will become 10 cos square 10 pi t minus pi by 2. So that's the same thing as 10 sine square 10 pi t. So we'll see that these are all oscillation graphs, but with certain phase difference. Okay. The oscillation of the first and second one is with a phase difference of pi by 6. So now when we look at the graphs of these individual particle oscillations, see that, for example, this one, it has a cos square graph. It varies with time periodically. So if our y is in millimeters, it varies between 10 and 0. So these are the extreme positions. The mean position is 5. Okay. And you can see that at this point, cos square is 0. So this term must be pi by 2. So this must be 1/20th of a second. Okay. And then this is 1/10th of a second. And then this is 3/20th of a second. 1/5th of a second. So you can see that the time period of oscillation, this this 0.1 seconds or 100 milliseconds is the time period. Okay. So frequency is 10 hertz. Now in comparison, if you just look at the oscillation of the other point, the one at x equal to 1 meter, you see it's very similar, but there's a phase shift. Okay. Now cos square pi by 6 is how much? 3 by 4. Okay, so it's like this. So you can see that the amplitude is 5 millimeters, not 10 millimeters, because extreme to extreme is double of amplitude. Okay? And time period and frequency are this. Okay? The same will apply here also, but just that this has got shifted. This is become 1/60th of a second. This would have become 7 by 60 per second. This would have become 1 by 60 plus 1 by 20. So that is 1/15 of a second. The time period still holds the same value, 1 by 10th of a second, but there is a phase difference. So these two have same amplitude of 5 millimeter, same time period of 0.1 seconds, but phase difference of pi by 6. You can understand that as the wave is propagating, different particles on the medium are oscillating with the same amplitude and same frequency, but with phase difference according to where they are located. For example, two particles located at x equal to 0 and x equal to 1 meter, they are having a phase difference of pi by 6 in their oscillations. Okay, so in comparison, you can see the third one is got a phase shift of pi by 2 compared to the first one. So this one and this one have a phase difference of pi by 2. So this also has the same amplitude and same time period. Okay, so now coming back to our general classification of equations. So the second type for the general equation y is f of kx plus minus omega t if f is a non-periodic function. So for example, we had that one. Okay, this. So y is equal to e raised power minus theta square. So this is a non-periodic function. So in that case, what happens? Therefore, then the given equation represents a traveling pulse, not a periodic wave. It is not a periodic wave. So it is this kind of situation that, let's say at t equal to 0, it was like this. Then after some time, it's like this. And after some time, it's like this. So you can see that this snapshot will be a single pulse. It is not periodic. So it does not have any wavelength. And the y versus t for a certain fixed value of x, it is the equation of a one-time kind of motion. It is not oscillation. So since it is not oscillation, time period, frequency, all these things do not exist. So that is the second category of this kind of general equation. It can be represented by a periodic function, in which case the general equation represents a periodic wave, which means that all medium particles are in oscillation with definite time period and amplitude. And the shape of the wave is also periodic, so there is a definite wavelength. On the other hand, the function used to represent it could also be a non-periodic function, like this exponential function over here, in which case it does not represent a periodic wave, rather it represents a single traveling pulse. So the motion of the medium particles is a one-time motion. Any particle goes up and comes down once as the pulse passes through that particular point, but it does not have a continuous up and down motion, so it's not oscillating. Yes. Okay, so we will hope this was clear up to this point. Right. So with this, we'll conclude today's session, people. Right. So we have understood, this kind of situation, the general equation, and how to bifurcate it on the basis of periodicity versus non-periodicity. Now, next time on the basis of this, we'll understand few more things from the general equation, more things to interpret, like particle velocity, not the wave velocity, but particle velocity, that is given by del y by del t, because it's the rate of change of the y displacement versus time. Similarly, particle acceleration is given by del 2y by del t square. Okay. These all kind of things we'll discuss about next time. And then we will move on to the general equation of harmonic wave, or the simple harmonic wave equation. So this will have an equation of this type. It's a sinusoidal function. So add any phase constant arbitrarily. So we will see this and its various properties. Okay, so you can start with H.C. Verma waves exercise, people. The first 15 odd problems from H.C. Verma's first chapter, which is waves on a string. So that's it for today's session. Wish you all the best and have a nice day.